adrenal cortex hormones. So adrenal cortex hormones are steroid hormones. So steroid nucleus, we have 4 rings, A, B, C and D. So A, B, C is a 6-member ring. So when you have a 6-member ring, 2 straight, another one is a perpendicular, that's called a phenanthrin. When you saturate this phenanthrin, that is called ferrihydrophenanthrin. So ferrihydrophenanthrin is 3 benzene ring, that's a saturated. So ferrihydrophenanthrin, that is a ABC, attached with D. D is a cyclopentane. So cyclopentanone ferrihydrophenanthrin, that is a steroid nucleus. So steroid, we have ring A. So the A and D, in between these 2 are chiral carbons, and B and C, these 2 are chiral, and C and D also, both are chiral carbons. The connection points are chiral carbons. So A and B, that's a trans stereochemistry, and B and C, the rings are connected with equatorial, that is a trans stereochemistry, and C and D connected with equatorial and equatorial, that is again as a trans stereochemistry. So AB ring connected with trans, BC ring trans stereochemistry, and C and D ring connected with trans stereochemistry. So it's a all trans stereochemistry. So first combo, this category is hydrocortisone. So the hydrocortisone available as a, mostly is available as a prodrug. So hydrocortisone, we have acetate, that is a prodrug, butyrate, prodrug, and butyrate, and cyclonate, and sodium succinate, and sodium phosphate, all are prodrugs. So the one, that lipophilic analog, that is a hydrocortisone cyclonate, is the one available as a suitable for tablet, and the second one, that hydrocortisone acetate, is available for oral and intramuscular, is suitable for both oral and intramuscular, and hydrocortisone butyrate, hydrocortisone butyrate, and valerate, those 3 are suitable for only the topical use, not for injection or tablet, only for topical. Hydrocortisone, there are 2 salts or prodrugs are water soluble. So sodium succinate is freely soluble in water, and the phosphate is freely soluble in water. So those 2 are suitable for only injection, IV and IM, not for tablet. So succinate is not suitable for tablet, and phosphate also not suitable for a tablet. Those 2 are suitable for IM and IV. So when you have a comparison, those 2 prodrugs, the phosphate is easily hydrolyzed than succinate. So when you see the difference for phosphate and succinate, the phosphate will give approximately in 10 minutes that the parent compound all are hydrolyzed to hydrocortisone, whereas succinate hydrolysis, it takes 30 to 45 minutes. So when you consider for the emergency use, the phosphate is more suitable because the fast hydrolysis of the phosphate bonds by phosphatase than comparison with slow hydrolysis with succinate by esterases. So the esterases hydrolysis takes like 30 to 45 minutes, and phosphates are hydrolyzed by phosphatase, that is fast hydrolysis, those are hydrolyzed in 10 minutes. So the one suitable for emergency is a phosphate as a prodrug, not a succinate. So there are 2 types of compounds in the market. We have a hydrocortisone and cortisone, even prednisone. One is a ketone, other one is a alcohol. So when you have this is a carbon number 11. Carbon number 11, hydroxy, that is a hydrocortisone. Cortisone, carbon number 11 is ketone. So this hydroxyl, the hydrogen is important for the hydrogen bonding interaction with binding of this compound to the glucocorticoid receptor. So when you change to hydroxyl to a ketone, the compound is inactive. It's not an active compound. So in the physiological system, the compound is converted, hydrocortisone converted to cortisone and cortisone converted to hydrocortisone. This is a reversible reaction. So it's an active compound to inactive compound and inactive compound to active compound. Then the reaction is catalyzed by 17 beta hydroxysteroid dehydrogenase. So we have two types of hydroxysteroid dehydrogenase, type 1 and type 2. So type 1 in the liver, type 2 in the kidney. So type 1 is a bidirectional enzyme. So it can convert active to inactive, inactive to active in the liver. So type 2 is unidirectional enzyme that is there in the kidney. So that is possible, it converts only active to inactive. There is no inactive to active conversion. It's a unidirectional enzyme. So the kidney enzyme is a unidirectional enzyme. That's a type 2 which converts the hydrocortisone to cortisone, not cortisone to hydrocortisone. So one direction, only unidirectional enzyme. The liver enzyme is a type 1, that's a bidirectional, which converts the hydrocortisone to cortisone, means active to inactive, and cortisone to hydrocortisone, inactive to active. So that is possible. And the kidney, so here is the excretion. We don't want to convert the active compound to inactive. That's why the kidney has only type 2, that's the unidirectional, which converts only active to inactive. For structure activity relationship, the trans stereochemistry, the one we discussed earlier, they are all trans stereochemistry that is important for activity. That's the AB trans. So the 5 and 10 carbons are trans, the 9, 10 is trans, and 13, 14 is trans, all trans stereochemistry. The 17 beta side chain, the 17 beta side chain is important. So that is a 17th carbon, the keto side chain is important for activity. Replacement of hydroxyl with fluorine, the 21 hydroxyl with fluorine, the activity increases. And the hydroxy replaced with the fluorine or chlorine, the activity decreases. So double bond in between carbon number 9 and 11, that is decreases the glucocorticoid activity. So whenever you have a double bond here, when you insert a double bond here, then the activity decreases. So the double bond 9 and 11 is not recommended. And 2 alpha methyl substitutions increases the activity. So when you have a substitution at carbon number 2, alpha methyl substitution, that increases activity. So when you have an alpha methyl substitution, that's serically hinder the metabolism of the third carbonate, that's the reason the activity increases. Reduction of 20 ketone, carbon number 20 ketone, that decreases the glucocorticoid activity because of that increase the hydrophilicity. So when you change the keto to hydroxyl at carbon number 20, the activity decreases, the double bond 9-11, activity decreases, and this methyl, alpha methyl and carbon number 2 slow down the metabolism, that increases the activity, and change of this hydroxyl with fluorine increases activity, and chlorine and bromine substitutions are decreases the activity. So the structure 1 is the hydrocortisone. Other one is the prednisolone. So the structure is almost similar structure, hydrocortisone and prednisolone. The only difference is the ring A we have there is no double bond, only one double bond, and here ring A we have 2 double bond. So when you have one double bond, the ring A adapts for the half chair conformation. We have 2 double bond, it is a flattened board conformation. So ring A is in a flattened board conformation when you have 2 double bond, and when you have one double bond is a half chair. If there is no double bond, there is a chair conformation, a circular exchange chair conformation is a stable one. So the hydrocortisone, one double bond, that ring A adapts for the half chair conformation, and hydrocortisone, prednisolone, 2 double bond in ring A that adapts for the flattened board conformation. when you have a comparison with binding with glucocorticoid receptor, the flattened boat conformation has a stronger binding affinity compared to the off-chain conformation. That's the reason we have 3 to 4 fold increase in activity for a prednisolone compared to patacortisone. So 3 to 4 fold increase due to the additional double bond that makes the compound ring a flattened boat conformation that has a good binding affinity with glucocorticoid receptor. So that makes the compound as 3 to 4 fold increase in the activity. So whenever you have a double bond, carbon number 1, 2, that is called D1 corticoids. So it's classified as a D1 corticoids. Means D1 means there is a double bond at carbon number 1 and 2. So the prednisolone prepared by the microbial dehydrogenation, that is the one which introduced the double bond at carbon number 1 and 2. The bacteria they use for the synthetic reaction is Corynebacterium simplex. The prednisolone compared with hydrocortisone, that compound has the 3 to 4 fold more active. The reason for 3 to 4 fold more active, the ring A adapts for the particular conformation, that is a flattened boat conformation because of the 2 double bonds, and makes the compound is higher affinity for glucocorticoid receptor. Oral bioavailability is 80% for prednisolone. Once it is metabolized, we get a hydrophilic, and those are less active metabolites. The major metabolites are 6 beta and 16 beta hydroxy metabolites. So 5, 6, whether hydroxy is introduced here or hydroxy is introduced in the 16th carbon. With the beta stereochemistry, those are possible phase 1 metabolic reaction, followed by phase 2. And then goes for the gluconide conjugate, those are water soluble and excreted. So phase 1 metabolites are less active, and phase 2 metabolites are water soluble and excreted. Acetate is suitable for suspension and ointments, prednisolone acetate. And butyl acetate is suitable for only injection, and that's compound is slowly hydrolyzed and suitable for the long duration of action. And sodium phosphate, that's a water soluble chloride. So you have sodium phosphate water soluble chloride. So that is suitable for injection formulations. The phosphates are easily hydrolyzed. We get in 5 minutes we get a parent compound prednisolone. Methyl prednisolone. So the compound has an additional methyl group at carbon number 6 with alpha stereochemistry. 6 alpha methyl substitution is attached. It undergoes for the extensive metabolism with cytochrome 3A4. So whenever you have a combination of 3A4 inhibitors, antifungals, ketoconazole or itraconazole. So when you have a combination of methyl prednisolone with ketoconazole, that decreases the metabolism of prednisolone, then increase the activity for methyl prednisolone because it's not clear, the compound is still in the physiological system that can potentiate the effect of prednisolone. So combination of itraconazole and any methyl prednisolone, that also prevents the metabolism of methyl prednisolone. So water soluble salt, the succinate salt is available. The succinate is fully soluble in water, suitable for IV. So when you compare the oral bioavailability, triamcinolone has a very low oral bioavailability, so only 23, and mostly triamcinolone is recommended for only topical, not for oral. The highest oral bioavailability we get for the hydrocortisone 96, and methyl prednisolone 90, and dexamethasone is a 78, and prednisone is 80 and 82. Dexamethasone, that's a compound has an additional methyl group. In the prednisolone, there is an additional methyl group, that is a dexamethasone. Additionally, there is a methyl group at carbon number 16 and alpha methyl group at carbon number 16. When you have a carbon number 16 alpha methyl, that is a dexamethasone, and alpha, this is a beta methyl, the beta stereochemistry. So beta methasone is beta stereochemistry, and there is a methyl, that is a beta methasone is beta stereochemistry methyl group at carbon number 16, beta methyl. Okay, stereochemistry is beta stereochemistry. The compound is exactly the same, dexamethasone. Instead of beta is alpha methyl, it's alpha methasone. So beta methasone, beta methyl stereochemistry attached at carbon number 16, and dexamethasone is the alpha stereochemistry. So the compound has the fluorine. So the fluorine helps for the compound potency. So when you have fluorine and an electron withdrawing group and takes electron from the lone pair from that's the 11th carbon, the oxygen, that makes the compound is more active. Additionally, the compound has a methyl function group. So the combination of fluorine and methyl that makes the compound 5-fold more active compared to prednisolone. So hydrocortisone to prednisolone 4-fold more active. Prednisolone to dexamethasone or betamethasone 5-fold more active. So when you have comparison of dexamethasone and hydrocortisone, is 5 multiplied 4 is 20 times more active. So dexamethasone is or betamethasone is 20 times more active than hydrocortisone. So we have a phosphate salt, those are the water soluble. So whenever you see the phosphate or succinate salts, those are not a tablets, those are only for a parental formulation. So the phosphate is really soluble in water and suitable for IV, and we know the phosphatase hydrolysis is fast. The compound is released within 10 minutes by phosphatase enzyme, plasma phosphatases. We get a parent compound, so dexamethasone. So beta and dexa is compound is exactly the same. This the potency also almost equal. We can say maybe the beta is little more than dexa, but the overall is equal potency. And the only difference is a beta methyl group, betamethasone, alpha methyl group, dexamethasone. So the potency, reason for the potency, the fluorine and the methyl group makes the combination of these two is responsible for the 5 times more active compared to prednisolone. Again is that both are D1 corticoids. Whenever you have a double bond, it's a D1 corticoids. Again, these two double bonds which adopts a platinum board conformation. So betamethasone, platinum board conformation. Dexamethasone also platinum board conformation for the ring A. Topical steroids, we have 3 of them here: peclomethasone, triamcinolone, and clobetasol. So far considered as clobetasol is the most potent steroid used for the topically. So the difference for here, peclomethasone we have a chlorine, and triamcinolone we have a fluorine. So the chlorine is the one responsible for the potency. When you have electron withdrawing group, chlorine, so it takes electron from the carbonyl carbon, the oxygen, hydroxy-oxygen. So when it takes electron from hydroxy-oxygen, that increases the dissociation constant for the hydroxy group. So when it increases the dissociation constant, that can make a good hydrogen bonding interaction with glucocorticoids compared to with chlorine, without chlorine, it makes a difference for hydrogen bonding interaction. So that is the reason this is more active. So when you compare with triamcinolone, triamcinolone is a fluorine. We have a fluorine instead of a chlorine. So it's a stronger electron withdrawing group compared to a chlorine. So the triamcinolone is more active than peclomethasone. The reason is we replace a fluorine instead of a chlorine. Fluorine makes the compound more active. So triamcinolone is more active than peclomethasone. Clobetasol is even more active than triamcinolone. The reason is we have a chlorine, and additionally there is a chlorine at carbon number 21. So this fluorine and chlorine combination makes the compound even more active. So the potency wise, clobetasol is more active than triamcinolone. Triamcinolone is more active than beclomethasone, and all are topical steroids, not for a tablet or injection, only topical use. The first one is a prodrug. So when you hydrolyze this ester, the compound is the active compound. Chemically it's a steroid analog, and it's a neutral, all are neutral compound. There is no acidic or basic functional group, all are neutral compound. And chirality, we have 1, 2, 3, 4, 5, 6, 7 and 8 chiral center. And this also 1, 2, 3, 4, 5, 6, 7, 8 chiral center. Here also 1, 2, 3, 4, 5, 6, 7 and 8 chiral center. And all are neutral. So we have the acetonide. The acetonide is this is the functional group, it's called acetonide. So the acetonide, reason for acetonide functional group, that it helps for the increase the lipophilicity. The most lipophilic is good for the topical use. So the acetonide is important for the lipophilicity, and that's good for the topical bioavailability. Fluorine increases activity compared to chlorine. Fluorine is more active, and steroid analog, chiral center 8 and neutral compound. And here we have two combination changes. One is the fluorine, and there is a chlorine additionally. These two combination makes the compound is more active than triamcinolone and beclomethasone. It's a steroid analog, and chiral centers are 8, and again it's a neutral compound. Spironolactam is a mineralocorticoid, binds with the mineralocorticoid receptor, and it has a diuretic response that increases the sodium excretion and potassium retention. And the keto group, carbon number 3, keto is important for activity, this keto functional group. And this lactone is important for activity. When you open the lactone ring, we get a hydroxycarboxylic acid. That activity is dramatically reduced the activity. So with lactone only the compound is active. When you hydrolyze the lactone, compound is less active. And 17 alpha substitution increases the intrinsic activity and overall activity. That is 7th carbon alpha substitution. That's a thioester. That is important for increase in the activity. It inhibitors for adrenocorticoid biosynthesis. So the corticosterone, those are biosynthesized from cholesterol. Cholesterol is the starting material for corticosteroid biosynthesis. So cholesterol is converted to pregnenolone and then followed by pregnenolone and then 21 hydroxyprogesterone and then followed by corticosterone. So the inhibition of conversion of cholesterol to pregnenolone, that is a enzyme called cytochrome 11A1. So the inhibition is that aminoglutathione can inhibit a cytochrome 11A1. So this is a corticosteroid biosynthesis inhibitor. Then another compound and metacaprid, that is a 11 beta hydroxylase inhibitors. So these two compounds inhibits the biosynthesis of adrenal cortex hormones, that is the hydrocortisols. So inhibit the biosynthesis of glucocorticoids. And the first compound is a aminoglutamide. So it's inhibit the cytochrome 11A1, and chemically is a weak base. There is a primary amine weak base, and there is no chiral center in the molecule. It's a achiral compound. Whereas this one inhibit the 11 beta hydroxylase, and chemically is a weak base. Those are both reading substitution. It's a weak base. Again, there is no chiral center. It's a achiral compound. So those two are adrenal cortex hormone biosynthesis inhibitors. One is the cytochrome 11A1 inhibitor, the other one is the 11 beta hydroxylase inhibitor. What's the right answer? C is the half chair conformation. A is right. A, C, yeah, A, C, D, A, C, D, yeah, not a B, D is not a D1 particle. B,
Can you go back again?
huh?
I didn't get the last.
This one? What is that? D. D is right. It's a it's not a inhibitor, it's an activator. F is right.
C.
C is right. One more. E is right. So C, E, F. So we have 13 questions in the final exam and 6 from today and 7 from the previous topic, the endocrine only, not a cardiovascular. So 2 from thyroid, 1 from diabetes and 1 from reproduction and 1 from hypothalamus, sorry 2 from hypothalamus and pituitary. You have
That's what we have. You only have 13?
total 40 was 27 that more and 13 that's all. He, after the exam he has a 3 hours, I have 1 hour. 40 questions, right? 13 and 27. That is the one we always common, 13 and 27. So 6 from today and 7 from the previous method. So you have any question?